Perfect. Thanks a lot, and good morning, everybody. So as stated, I want to give you an overview of the capabilities that we've developed at the European Space Operations Center in Darmstadt, Germany, with regards to future lunar missions. And actually, I want to dive right into the topic. I have an overview slide at the end where you see the whole picture how it comes together. So we start with terrain modeling. I think this is something many of you are familiar with. So we're using basically the AIM stereo pipeline provided by NASA to generate high resolution models of areas of interest. So yeah, we're basically using a lot of the data provided by the Lunar Reconnaissance Orbiter there, and then go through the whole process of selecting the images, adjusting these images to another and to an underlying LoLa dam, and then using, depending on the sites, photoclinometry or stereogrammetry to derive these dams. I won't go into full detail here, as this is a process, I think, well established, well documented. I think the relevant point here is that we are producing with that. So if we're using the shape from shading process, we're using one of the results is local dams of 1 meter per pixel scale. We've done this up to 10 times 10 kilometers for now, with the only limit being actually calculation power, but we could go larger if of interest, but usually that covers quite a reasonable area of interest. Nice byproduct is these maximum lit mosaics, as you can see on the top right, for one of the preliminary sites of interest for Argonaut. And yeah, obviously deriving from these terrain models, you can get high resolution slope maps as well. And our main use case is actually these terrain models to calculate the local horizon. So what we're doing is basically understanding how would the local horizon look like standing at any point on the lunar surface. For that, we're using actually usually 3 different dams, because we have to look up to, let's say, a distance of maximum 220 kilometers in the distance to catch even far hills that might contribute slightly to the overall horizon mask. So we're using that for the far distance. For distance up to 10 kilometers, we're using the LDAMs that were already presented here. So depending on where we are in the South Polar region with a resolution of 5, 10, or 20 meters. And then the local shape from shading dam we use really for 1 kilometer surrounding our site of interest. And how it looks like basically is that we're scanning the region. I hope you can see the red dots over there. So we're basically scanning in 1 degree azimuth steps all around the site, understanding what is the highest elevation in that direction. And this marking basically our local horizon there. Now, as you may see on the bottom part, so in this region, and up here, we can't see any red dots. I hope you can actually see them at all, which is because this is only the GLD 100, but if we zoom in, we can see that the defining topography for the local horizon for our landing site over here is actually either the green or the blue dots. So this is the LDAM and the shape from shading dam. So it's rather the local topography being very close by. And this is why we're using these different dams, because it might be that a very small hill nearby is defining, or a large mountain far away. And if you combine all of this, what you get in the end is, as I said, the local horizon mask. So you get at this point from 0 to 360 degree azimuth, depending on the local north, you get how the topography would look like. And okay, the main use case for that is already forecasted in this image, because what you can see in yellow is the position of the sun over an entire year. In this case, it's the year 2030 that we looked at. And in blue, the position of Earth over 1 year, wobbling around this roughly 90 degrees azimuth, which gives you a rough idea also of where we are in terms of sight. All right, and this brings me already to the visibility analysis. So what we're using these horizon masks for, basically the idea is rather simple. You extract from the ephemeris the position of the sun, the Earth, in the future, the gateway, or any artificial object that there is in space or on ground. So we have looked at the potential moonlight satellites. We looked at specific ground stations on Earth. We could look at any lander or any asset that is on the lunar surface to understand time-dependent visibility over there. And then just basically check azimuth and elevation. Is the elevation higher than the local horizon mask at that angle? Okay, fair enough. We see the target. Is it lower? We can't see the target. And yeah, this gives us then time-dependent plots. So here you see it for the year 2030, Earth on the top, quite regularly, observation windows, and the sun on the bottom, being very much irregular, with a local summer where we have a lot of visibility and a local winter where there's not so much visibility because it's just at the edge of the horizon due to the low elevation. So this is the time-dependent data, if that's of interest. If we're looking more on average visibility statistics, we are able to produce them. So on the top, we have, it's a bit dark, unfortunately, a view of the average sun visibility around the whole lunar South Pole. And on the bottom, just for the area of 1 × 1 kilometer around the site 4, one of the sites I picked as a preliminary site of interest for Argonaut. And yeah, so here we have average visibility, we have longest shadow. There's really any statistic you're interested in, we are happy to look at. And this all comes together in the site selection, and it's a bit maybe more complicated if you look at it the first time, and I hope I'll be able to walk you through this. Because what I've described so far is only looking at a very single site, a single point on the surface within your grid or whatever you want. But if we're talking about a 1 meter spatial resolution, we won't have a lander of the size of 1 meter, and we won't be able to pinpoint it at that specific site 1 × 1 meter. So what we usually do is we do this for a couple of sites in a certain grid, and now we look for a feasible footprint. Let's say we have a lander with a diameter of, I don't know, 3, 4, 5 meters, which obviously gives us that we need a couple of pixels or grid points to meet our requirements. These requirements might be, we want to have an operational window of, I don't know, let's say 10 days. All right, so we want to have 240 hours of continuous sunlight and continuous communication to Earth, direct or via a relay satellite. Now, the important point is that this is on different heights, because the solar panels might be at a certain height and the antenna might be at a different height. So all of the calculations we're doing with the horizon mask is height dependent, right? So whatever height is of interest, depending on the lander that you choose or that you might choose, we can look at these different heights. And then we can say, for each point in time, do we have at a certain height of the solar panels continuous illumination, and at a certain height of the antenna continuous Earth visibility or relay visibility? And then we can say, okay, this is a mission window. Yeah, we take the slope analysis also into account, because usually we have a constraint on the slope that we're able to land. And this marks for any epoch a pixel as feasible or infeasible. And then we group them, as I just stated, to say that we have a feasible footprint. This is actually where the lander could touch down, because all of these pixels fulfill the requirements at the same time. And then we go one step further, and this goes really far into the engineering. We're looking at what we call the horizontal redirect, because usually what the landers have and what we've seen in the past is that at a certain height, let's say 50 meters or something above the surface, the lander will come to a rather full stop, scan the surface below, and understand, based on pre-computed maps and the images it takes, where to land. And the important fact here is that actually for the entire area that we scan there, it doesn't need to be that the entire area is feasible to land. In this case, we wouldn't need redirect because we could just touch down. But rather, we want to have at least one feasible footprint within our scanning distance and redirect capability, right? So if we have the capability to redirect, in this case, 40 meters is the medium one, then we could reach this feasible footprint from our center. And this marks, and I hope you can still follow me, this marks it as a feasible descent point. So if we come to a stop at this specific point, we would be able to touch down at the feasible footprint because we can reach it. And okay, if we do this again for all the points, then we get a large area of feasible descent points. And this is where it comes to the landing accuracy that you often hear for landers who say we can land within an accuracy of 50 meters or 100 meters. In the analysis I'm presenting today, we understand this not actually as the landing accuracy, thank you, but rather as the accuracy of this full stop that you have at a, let's say, 50 meters height. And obviously, then depending on the analysis you want to do, you know, okay, this is the required area, the required landing accuracy I need, or this is a feasible site because I fixed the landing accuracy. Something I want to show you here, which we've done for one of the sites for Argonaut of preliminary interest. Please don't understand them by any means as reference or candidate landing sites. That is just preliminary sites of interest, and there's a lot of them. I just picked one to show you. So what we have here is for 3 different redirect, 20, 40, and 60 meters of horizontal redirect, the required landing accuracy. So here we have this as an output parameter to understand which required accuracy do we need to land in this region. And what we can see is that for 20 meters redirect, well, there's rarely regions that go, you would need an accuracy of something between 50 and 75 meters. But if we increase the redirect capability to 40 or even 60 meters, we can see that the areas open up and we actually don't be that accurate on the targeting because we can redirect a lot, which I guess makes sense. Other point is that if you have a fixed landing accuracy, you can directly detect where can you land, and then you're able to evaluate these sites and score them based on whatever scientific criteria you have, or maybe on safety aspects. So there's a lot of analysis going on, also for prospect, what we're going to hear later on that I'm not able to touch here right now. But basically, there's any analysis you want to do in terms of finding the landing site that should be possible with that. Here's the complete overview, basically summarizing what I've just said. So we're generating the dam on the very high resolution around the area that we are interested in. We calculate the local horizon mask, compare this in the visibility analysis to the position of sun, earth, or any artificial target there is. And yeah, then have time-dependent visibility. We look for mission windows, whatever the constraints are, depending on the different heights. And in the end, we come to the landing ellipse analysis, either understanding which landing accuracy is required or having a fixed accuracy because we know which lander it will be, and then look at which sites we can land and which might be more valuable in terms of science and safety of whatever there is. And yeah, we're developing all of this for the moon mainly, but obviously there's clearly application also for Mars and other targets. If the interest is, we are looking always on the long-term plan also to execute this on other planetary surfaces if the data is available, of course. So I want to close with that, a list of a couple of supported missions or mission studies that we're working on. And yeah, the team, because I want to say this is not only my work, but the work of the section. It's in the mission analysis section at ESOC. We're usually doing the trajectory analysis, the orbital dynamics, and now we're also looking at the surface and are working on that. Thank you very much. Yeah, are there any questions? Does not seem to be the case. Right, there's one.
So how often do you produce new landing site analysis? Is that a regular cadence that you have, or do you work with ESA to identify priority sites? Kind of talk to us about how, let's say a lunar lander company wanted a landing site analysis. How might one engage with you and go, could you look at someplace for us?
Yeah, so to answer the first part, I mean, we're looking at quite a wide variety of sites at this stage, given that Argonaut is still a couple of years ahead. And so there is, let's say, quite a lot of work going on very different sites. If there's of interest in this analysis and some service that could be provided for a specific site, I mean, I'll be around so we can exchange contact details. Otherwise, it would be the head of the section, Florian Renk at ESOC, to directly contact and ask us. And overall, we are very happy to share this. And one thing I should mention is that we are also targeting overall to eventually make this software publicly available, right? So because we really want to enable the European community also to be able to analyze the surface. And right now we don't really see a commercial market over there, so which is why we're keeping this and developing this. But if it arises there, we are open for any possibilities there. But if there's imminent need of any service, we are very happy to provide this for sure. Yes.
Thank you.
Thanks a lot.